Okay, we are continuing on with unknowns, and not a lot of general stuff to tell you. I want to remind you that there is a document in the unknowns folder that is, what do I call it? Helpful stuff to remember for unknowns project. Has anybody found that yet? Anybody know this document I'm talking about?
I think so.
Okay. Start looking that over. You know, give it a few read-throughs, because there's just like little things to sort of be on the lookout that, you know, if you already have them in your head, when you encounter them, it'll be all the more salient. Okay? I'm going to add on a couple, I think 3 or 4 more of the qualitative tests, and then I'm going to leave a few of them, like I think 3 of them, including boiling point, till next time, just because I don't want to talk too long. I don't think it's 2 now, quite too long. Yeah, and then, so after today, we still have 3 more times. This goes a lot faster when there's only 8 of you per class. Just everything is going faster, so it should be plenty of time. I will start meeting with you next time and have a meeting. I expect I will meet with each of you at least twice, so I can meet with the whole class next week, and then, you know, probably the whole class the week after. And then if somebody's really just lost, I can meet again, even that 3rd week. Okay? Sound like a plan? Okay. So, general info. Read helpful stuff to remember or unknowns. If you suspect your unknown is a neutral compound, okay, do the DMP test. DMP test is a really nice sort of divisor. Okay. If it's positive, then you know you're going to ketone or an aldehyde. If it's negative, and you really are among the neutrals, and that can be neutral down here with sulfuric acid, that's how you got there. Or it can be neutral, water-soluble neutral. Okay? So you do the DMP test. If that comes out negative, then you know it's an alcohol, an ester, an alcohol or an ester, right? Yeah, alcohol or an ester. Okay. And we're gonna. We don't have, if you haven't figured it out, we don't have a test for esters. You come to the conclusion that you have an ester really by a process of elimination. You rule out ketones and aldehydes and alcohol. Okay. More fall tests. Okay. All right. First one I'm going to do is bromine. Okay. Now, we're going to see that a lot of tests have what we call false positives. False positive is a positive, you get a positive, but it's not really a positive for what you're looking for. Okay? A false negative would be, it really should be positive, but for some reason the test came out negative. Okay? So you've missed something that is what you were looking for. False positive is, you suspect it is what it is, but it's what you were looking for, but it ain't. Now, so a lot of these qualitative tests are going to have false positives. Bromine has a couple of false positives, including, or I guess the primary one, and some people don't even call it a false positive because you still do gain some information by it. First of all, so it's for alkenes and alkynes. Okay? It is bromine. A bromine solution has a very dark reddish brown color, and so you're going to add it. Okay? If there's nothing for the bromine to react with after two, sometimes it can react with water or impurities, but if you add more than 2 drops, okay, and the color doesn't go away, the color stays there, that means there was nothing to react with the bromine. Okay? And so you can conclude, I don't have an alkene or an alkyne. All right? Or I should say I have evidence to suggest there is no alkene or alkyne. Okay? Bromine can react, as it turns out, okay, and the color disappear with some aromatics, what we call activated aromatics. Okay? The things that tend to be really strong ortho-para-directors. Okay? And so, and the test is a little bit different. With alkenes, the color goes away. Okay? With superactivated aromatics, the color goes away, but you also get fuming because you get a different product. You actually create gaseous HBr, and you can hold a wet pH piece of pH paper above, sort of where the gas is coming up, above the test tube, or sort of right at the mouth of the test tube, and if HBr is being created, it will turn it red. Okay?
So would phenol give that false?
What's that?
Was it phenol? Phenol? Sorry.
Phenol, it could. It could. I can't promise you one way or another. I don't know off the top of my head, actually.
Possibly.
Yeah. Diphenol. Diphenol. That's a different name, but I'm blanking on it right now. If you have 2 OHs, I don't think you've talked about this stuff with Dr. Horgan yet in Dr. Horgan's lab. Okay. All the ortho-para directors are what we call electron domain. Have you discussed electron domain and electron withdrawal? Okay. In any case, I certainly have taught you guys how do you recognize an ortho-para director. You had to do it for your report that's due today, right? Ortho-para director you recognize because there are lone pairs on there, or it's an alkyl group. Okay? All the ortho-para directors are electron donating. They push electron density into the ring. Electron donating will make it react with high electron donating groups, can make it react with bromine even without a catalyst. Okay? Except for halogens. Halogens are actually electron withdrawal, but that's a subtlety that you don't need to get into. But even though they're ortho-para director, they're electron withdrawal. In any case, if the color disappears, and if it turns the litmus paper red, okay, you have some decent evidence that you have an aromatic and an activated aromatic, one with electron donating. However, that would be a reasonable thing to suspect. However, if you think, you put it up there and you don't get the red, don't jump to the opposite conclusion. Don't jump to the conclusion, I don't have an aromatic that's activated. It might just not be activated enough. So it's a weaker test. The alkenes is pretty cut and dry. If you got an alkene, it's going to give you a positive test. If you don't got an alkene, it's not going to give you a positive test. Does that make sense? So it's just sort of the, the classic bromination mechanism that we've already looked at a couple of times. so this is reddish brown, okay? And this is colorless. All right. Okay, so how does this happen again? All right, we know that halogens can behave as electrophiles. Yeah. Or it does this wacky thing where the alkene attacks the bromine. It's going to abandon one of those carbons, make a carbocation, but in the process, one of these lone pairs bites back down on it. It also kicks off that bromine in the process, or bromine, I should say. What that generates is what we call ammonium. Okay. Here's your bromine. And this attacks one of the carbons of the bromonium. If one was more crowded than the other, it would go for the less crowded, but here it doesn't matter. Okay. And that's how you get that. Okay. All right. Oh, yeah. Okay. Including thoughts. If reddish brown persists after 2 drops, and it's a negative tau. Note some activated means it's got electron donating groups, aromatics can react. Oops. Okay. All right, so what would that look like? I'm going to put a generic group on here. I'll put a pi on there. Let's give it a lone pair just for the heck of it. Let's make it aromatic. Bromine. Different reactions, not an addition reaction, it's a substitution reaction. HBr, that's the key product that you detect. Okay. Similar type of mechanism. Oops. Or at least for parts. Okay. We get.
Is that supposed to be VR2 instead of just VR?
Yeah. Okay, get that in here. I want to remind you that there are other resonance structures. I'm not going to draw at the same time. Okay, so that's just me reminding you there's other resonance structures. Under the conditions that we did this, the only base that's around, appreciably, is bromide. Okay? And this wants to be aromatic again so badly that bromide actually can behave as base in this context. Grab this electron. Right there. Boom. Okay, so fogging acidic gas. Okay?
And then this is the red influence, or the pH version of red.
Yeah.
Okay.
Yeah, that's how you detect it's acidic. The fogging is one clue. Okay, oh, I see fogging. Just a regular alkene isn't going to do the fogging, okay? Because you have, you know, it's there's no HBr created as a result of the reaction. Okay. This can be good confirmation for an activated aromatic. AR is an abbreviation for aromatic, AR. Can be good confirmation for an activated aromatic, okay? But not good exclusion. Okay? So, if you don't get a positive test, that doesn't mean you can exclude the possibility you have an activated aromatic. It just might not happen every now and then. Okay? That's why I tend to call this more of a false positive that gives you good information sometimes. Okay. All right. Squeeze in potassium permanganate. And potassium permanganate is just sort of confirmation of alkene or alkyne. Okay? So we have two tests for it. They're both very easy tests to run, so you know it's worth having them in there. If they were both very involved reactions to run, maybe we think about excluding one of them because it is a little bit redundant. Excuse me. This is also known, by the way, as the Bayer test. Okay. So these, by the way, these alkene and alkyne, is that one of our primary functional groups, or is that one of our subsidiary functional groups? Subsidiary. Okay. So we could have lots of them, we could have none of them, etc., etc. So the Bayer and the bromine test, along with Beilstein and ignition soot, you should do that on all your unknowns, or both your unknowns. Okay, make sure you do all four of those on both your unknowns. Okay, how does it work? I'm going to do a little hand waving. Part of it. I'm drawing a very funky. I did a terrible job. That's supposed to be cyclohexene. That's supposed to be the same molecule as over there, but I wanted to draw it on its side. I can't even look at it. It's just so. Try that again, Bert. Not much better. Okay. Anyway, let's give up. I wanted to do this to help remind you, not really pertinent to the unknown project, but pertinent to the chemistry. I wanted to remind you that, do we call this type of addition, oh, gosh. I made a mistake on here. Does anybody know the mistake I made here?
It's supposed to be indifferent.
It's supposed to be opposite, right? because this is anti-addition, right? The reason why it's anti-addition is here, because of backside attack. It's analogous to an SN2 reaction. So since these guys are sticking at me, it's got to go to the polymer. Okay. So that's syn addition. I'm sorry. Come on, Bert. You can do it. Anti-addition. This is syn addition. And it's syn addition because we're going to create a cyclic intermediate here. Okay, so it's going to make a ring with those two carbons. And it can't make a ring on one side of the alkene and then come up here and connect to the other side. It's got to connect from the both sides, bottom or above. That's why I'm showing you the super ugly cyclohexane. Okay. So it's kind of an unusual mechanism. You get an attack of the alkene. The alkene is also simultaneously attacking that oxygen of all things. Okay. That puts that electron pair on top of the manganese, and that puts those electrons up like that. Let's see, how do you do it here? Well, I know where I'm drawing, so manganese, what you end up getting, manganese dioxide. This is purple. Okay. And if the purple sort of disappears and you get a brown precipitate, that's positive Chem. Okay. This last part is, this intermediate is just basically hydrolyzed water. Little hand waving on that last step. Okay, for this test, there are lots of false positives. Potassium permanganate is a very reactive chemical. And some of those false positives means aldehydes, okay, benzylic or allylic alcohols. Okay. Do you remember what benzylic or allylic means? A benzylic alcohol would be an alcohol where the OH is not on the aromatic ring itself, but on one carbon removed. Okay? It's right here. Then it can react with potassium permanganate. Aldehydes, certainly. Amines, certainly. So forth. Okay? So, if we were going to get rid of one of these tests, because of all those false positives, we'd probably get rid of that one. Because probably the bromine test is a little more reliable. Okay? But one nice thing is that it may not react with an activated aromatic compound, depends on what the activating group is. So, if the reason why your bromine test is positive is because it's an activated aromatic, not an alkene, okay, then you should get a negative test with that. That could be some evidence to suggest that you have an activated aromatic. Or conversely, if you I got a positive bromine test, I don't know about the fogging business, gosh, Am I sure it's an alkene, or could it still be an aromatic? Well, if you got a positive bromine test because it's an alkene, it'll definitely react with this one. Okay? All right. Any questions so far? Making sense? All right. Just a couple more.
To distinguish between an alkene and alkyne, you just use the NMR and IR.
Yeah.
Okay. 'Cause
Yeah.
there's no
And mass
difference.
spec too, right?
Yeah.
If your suspected compound is an alkene versus an alkyne, it's going to have a different molecular weight by 2.
So there's nothing on these two tests that can distinguish.
No,
Okay.
not really. Okay. All right. Ferric fluoride test. Okay. Test for phenols. Some of these tests, by the way, have a couple different solvents to do the test in. And that's because, different unknowns might not be soluble in different solvents. I can't remember, I think for this particular one, there's 2 different solvents that are suggested. You can do either one, actually. Is that right? Does anybody have the thing in front of them? Does anybody have the ferric fluoride? On your procedure sheet.
It says unknown with H2O. You can also do this test with 70% ethanol.
Yeah. So there's a lot of your compounds that aren't very soluble in water. In fact, we would actually predict if you suspect it's a phenol, it's because it wasn't soluble in water. So the 70% ethanol will definitely work and dissolves a lot more than just plain water.
Same volume?
Yeah. Okay. Ferric chloride is iron trichloride. And you get kind of a wacky adduct. To abbreviate, I'm going to abbreviate this benzene ring as pH. Okay. Capital P. You actually get 6 of these phenoxy groups around iron 3. Okay? Plus HCl. Okay. And this guy tends to be vibrant color. And then down below I'll list the color possibility. All right, so in the beginning, it happens by iron trichloride is a Lewis acid. Okay, so the lone pair here of your alcohol, or of your hydroxyl group of your phenol is attracted. Yeah, I should draw this out. Sorry. So it basically does what's like an SN2 reaction on iron trichloride.